Greetings everybody, this is section 3.2's lecture. We're introducing the concept of functions. The things we'll be going over in this section are relations which have parts, which are called a domain and a range, special relations called functions, when they are graphed functions pass the vertical line test. Functions use a special notation that uses parentheses differently than other expressions called function notation. And then we have some vocabulary that we'll pick up along the way. The independent variable, or the input, has several different ways to refer to it. Sometimes it's the variable x. Likewise, the dependent variable has several terms, and sometimes we refer to it as the variable y, although you don't have to have x and y. We'll start with relations. Basically, a relation is any, and the emphasis here is any, set of points in the plane. A relation does not have to conform to any rule. So, for instance, a relation does not need to pass a vertical line test or a horizontal line test or a reflection line test. A relation can be a doodle. So, for instance, here's a relation. So that could be your relation R. A Jackson Pollock drip splash canvas where you take the paint and you just splatter it all over the place. Now, if you have an original Jackson Pollock, do not turn it in as your math homework because it's probably worth $1 million to $3 million now. A vertical line can be a relation. So, for instance, if we have, I'll freehand this because my protractor went over there. If we have that could be a relation. The set of all points in the plane, if you were to think of coloring every single point in the plane blue, then you've made a relation. Now, a relation is a set of points. So for over here, just for an example, I drew a relation R as the union of a handful of line segments. The domain of a relation is the set of all x values. So that means that if you have an x on the x-axis and there is a point in the relation with that value of x as x coordinate, then that x is in the domain. Well, what that means is, starting from the graph of the relation, if you can move vertically in either direction to the x-axis, then you have found a point in the domain. So in essence, the domain is like the shadow of the relation on the x-axis. Just start with your relation, wherever you can move to, wherever you can move to vertically on the x-axis, and I'm shading it here now, that is the domain. It's the set of all x's that show up in the set of points in the relation. So there is the domain of this relation. And we very often abbreviate, we use a capital D for domain, and we use the name of the relation as a subscript just to save some writing. Now, the range is the set of all the y values. So that means if you start at the relation and move horizontally to the y-axis, then you've located a point in the range. The domain lives in the x-axis. The range lives in the y-axis. It's the set of all y values. So we can project this range back over to the y-axis, and we would end up with a lot of points projecting, infinitely many points projecting over to here. 1 point there, 1 point there, 1 point there. A whole bunch of points projecting over here, 1 point here, all of these guys coming from the right. And then finally, up at the top, there would be infinitely many points being projected in both directions. So this is the range of relation R. Now, functions are a special type of relation. The important thing about functions is that they are the central object of study in Math 107. We start off in Chapter 1 looking at functions specifically, and then we recast all of algebra in terms of functions. It's the major unifying idea in college algebra. So functions are a special type of relation. The main idea is that your x is unique. That means each x can only be used as the coordinate, the x coordinate of one point. Each x is the x coordinate of only one point. So what that means, if you've got the graph of a function, if you pick an x here, if this x is in the domain, I'm only allowed to use it once. I can only put 1 point above that. So I can put a point here, but that's all I can put. So I could say like x comma 2. That makes it look like x is approximately 1. I can't do a point here and then a point above it or below it. And that gives us the vertical line test. The fact that each x can only be used once means that there are never any 2 points on a vertical line. Now, if you pick a point that's not in the domain, then there is no corresponding point in the relation or the function, so you'll have 0 points. It's okay to have 0 points. If it's a function and x is in the domain, you will have 1 point, but you can never have 2 or more points. We've developed this traditional way of looking or writing down functions because functions are relating to variables. That is the major idea. The function value is the output. So the entire group of 4 symbols here represents the output. We often associate the output with the variable y. Inside is a place to put the input. The place where we put the input is often called the argument. Now, this x here really doesn't quite act like the normal variable x. This is just a place to put the input. In fact, we often call it a dummy variable. I like to think of it as an input slot or blank. So I think of function notation like this: f of whatever equals whatever. So I just think of what that x is representing a blank to fill in. Okay. Now notice how that we pronounce this a special way. This is f of x. That is almost the universal pronunciation in at least English. Now something important, even though we're using parentheses, this is not multiplication. These parentheses are, all they're doing is saying, here is your input. this is where you put it in. This is how you recognize the input value. In fact, I go to special effort to try to stomp out a math myth here. Depending on how you number your math myths, there are several hundred of them. Parentheses do not mean multiply. You, as of now, have officially encountered 4 different meanings for parentheses. We've already seen that they can abbreviate an open interval. Open interval means it does not contain its endpoints. So this is a set of things on the number line between -2 and 5. It can also represent an ordered pair. These exact same 5 symbols, actually I guess there's 6 symbols there, can represent an interval on the number line and a point in the plane. There have been various attempts to try to change the way we do notation to get rid of exactly this ambiguity. We've just encountered in function notation. The parentheses, all they do is they surround the input, they delimit it. There's no multiplication there. Then finally, one of the earliest uses of parentheses that you probably saw were in grouping. Here we have parentheses grouping a pair of binomials. Without the parenthesis, if you just drop the parenthesis off, you would have this. And an x times an x equals an x squared. And since multiplication has a higher precedence in the order of operations, that multiplication would go first before the subtraction, which is not what you wanted up here. So even here, the parentheses did not mean multiply, they meant group. Juxtaposition, bumping 2 things side by side, means multiply, and that's exactly what happened right here. This was a case of juxtaposition. That means multiply. Parentheses only group.